Yes.
Dr. Chapman, he can run late.
He can go later.
What's going to happen?
Okay, so as I said, we're moving into the field of physics, and I am very pleased to bring to the podium Dr. Eugene Chaffin. I met Gene when I worked on the RATE project, and he was able to certain of the of his formulations and understandings were so advanced we couldn't. I don't think anybody else understood, particularly when he's talking about Calibi-Yau space and some of these things, which were amazing. I think the idea is that the changes that caused accelerated decay were actually universal, and that's what we're talking. Maybe it happened in stars. It didn't just happen just on Earth. It happened in Mars and everywhere else. But exactly how that could happen and the effects and those things are the bailiwick of our next speaker, Gene Chaffin. So I'll let him take over at this point.
Thank you, Steve. So I've titled this "A Creation Physicist Questions," and I'm going to try to deal with what Steve asked us to do. You know, divide our questions into bulwarks, and that would be things that we know for certain, and some things that are not quite so certain, and on down the list there. And I'm going to deal mainly with things that I call my own type of physics, and I'm not going to get much into geophysics. That's for John this afternoon, I guess, and or atmospheric physics. That would be for whoever's doing atmospheric physics today. But I want to stick to my background because I'm more confident working there. I recently got an email from, I'll call him George because I don't want his name to be out there on the internet. He's a citizen of an East European country. Let's just say that, okay? I could give you specifics privately if I think I trust you, but he wants to major in geology, and he's at an Eastern European university, and he told me by email just exactly what you see on the screen. I just copied and pasted there about what happened in his first day of classes. He said, first thing that was said in introduction to all courses is that God doesn't exist. And further than that, in the introduction to geomorphology course, the teacher said that man-made global warming is truth. And I tried to caution him. I didn't think he'd get his degree if he disagreed too much with his teachers, and I think maybe some of what I said might have stuck. And he said, I kept my mouth shut. Arguing with teachers isn't a good thing. Okay, but this would be one of the certainties. We Christians know, if you're a child of God, you know that God exists. Whereas I don't think his teachers know this. They need to find that out, and hopefully there can be a balance there where he can witness to his teachers but not get thrown out of the university, which could happen too, I guess. I don't know what will happen in that situation. I would be scared if I was that student. Anyway, all right, there's a part of physics that depends on these diagrams that are shown here on the screen. They are called Feynman diagrams. And when I was a graduate student, there were two of the faculty who taught a course in which they taught us how to do these things, how to do the math and come up with answers, numbers, out of these Feynman diagrams. And that wasn't my main thing in graduate school, but I did take that course. And recently I've been trying to get out my notes, which I still had stuck away in a file cabinet, and do some Feynman diagrams because they affected my creation research. But one thing that I recall is that there were a lot of infinities in this branch of physics, and the prevailing theory is that these infinities cancel out and you only have to use the diagrams which connect to infinity. So you see the diagrams on the left here have lines that go off to the bottom and off to the top. Sometimes the Feynman diagrams are put sideways. That's becoming more popular in recent times, and you have to go from left to right. But in Feynman's original way, in his original papers, it was bottom to top. And if the lines go from bottom to top, then that's then it has real particles in it, not just virtual particles, and you should get numbers which can be measured in experiments. But there are also these bubble type diagrams that as you see on the right, that one that's over here, an unlinked bubble, and that can't be used to calculate anything, okay? These unlinked bubbles lead to infinities, and these are the kind of things that are supposed to cancel out. And why did I put this up here? Well, because as this talks about, there are fluctuations always taking place. In order to find a real process, a scattering amplitude, you have to divide by the contribution of all of these unlinked bubbles, and which evidently produces only a multiplicative factor for the connected graphs of interest. Okay, so by the time you do what's called renormalization, you don't need these unlinked graphs anymore. You just throw them away, because that leads into how you get the real value of the charge of the electron and questions like that. Okay, and so we could compare this to what we do in creation work. Okay, thank you. Thank you. This, okay, so you have this unlinked bubble here, thank you. And when we're doing creation research, we might get into projects where they're just like unlinked bubbles. They don't lead to anything that links us to mainstream science. They may help us to understand, what's going on when we think about the Bible and how I'm supposed to think about it internally, but it doesn't lead to anything that a mainstream scientist, let's call it, the conventional science, the person who doesn't believe the Bible and he just goes to university, learns how to do Feynman graphs and spends the rest of his life doing them, on computers or whatever, that we can't relate to him because we're doing research that isn't testable, doesn't have any testable consequences. Okay, and so I'm trying to tell you that we should probably concentrate on the type of diagrams which are on the previous slide. These diagrams over here, as being symbols of research that really connects with what the world is thinking, so we can change the world. Right? That's what we're trying to do. We're trying to make creationists out of more people. We know we can't do it for everybody. There's always going to be evolutionists. But we'd like the paradigm to shift a little bit, wouldn't we? Isn't that our goal? And so we want to come up with questions that matter. Okay? Now, one thing that I think matters is what the RATE project was about, which Steve and John and I were in the mainstream of that back in that day, and I guess we still are. Accelerated decay is something that must have occurred. We know this because there are lots of evidences, whether you want to talk fission tracks or radio halos or whatever, there are lots of evidences in the rocks that seem to indicate that a lot of radioactive decay occurred. There are some creationists that I know that are still resistant to that idea, but in my mind, that's a subtle thing. There had to be accelerated decay. Okay, and but there are some questions that we need to answer, like, is the same mechanism for alpha decay responsible for the acceleration of beta decay? Since there are different processes, when a physicist calculates them, you have completely different math, and so how could they have the same mechanism? Or is there something, like change in physical constants that affects both? And that's an important question. Okay. Now, in quantum mechanics, the alpha particle wave function is a quantity whose square gives the probability density for finding a particle. Okay, that's the modern accepted way of how we calculate things for alpha particles. Okay, we use this wave function. And if the strength of this so-called strong nuclear force were to change, then the way that the alpha particles held inside a nucleus would change, and it would change the alpha particle wave function. So the wave function is like this squiggly thing here, and this other graph would be a model for how the nucleus affects the alpha particle, how it affects the wave function, okay? And if there's a change, say, in the depth of this potential well, then the number of nodes in the wave function could change. As shown here, you see there's a dip going down below the axis right here on this wave function, but not over here. So you've had a change in the number of crossings of the x-axis here, a change in the number of nodes. And that can drastically affect the probability that the alpha particle comes out of the nucleus, which is the probability that a decay of the nucleus will occur. And that, by counting these decays, that's how we come up with these age estimates. Okay, and so that's the wave function is connected to that. So there's an experiment where you vibrate a string on a let's see, maybe my animation isn't working here. Let's see. I see the little circle going here. Well, you have a string between a clamp and a vibrator over here. You can do this in introductory physics lab, and if this string is clamped at this end and vibrated on this way, and you can make it vibrate by this vibrator, and you can form a pattern here. But if this clamp is a little bit loose, then some of the wave action will get outside the clamp and come out here, and that could be analogous to what we're talking about with the wave function in quantum mechanics on that previous slide. Now I've got an hourglass here and it hung up on me. I had it animated. There it went. Okay. Let's see. Okay. Well, not everything works the way you wanted it to. I'll just go on. I think it will. Okay, now just.
Is that this one here?
Yeah. Well, go past that slide first. Yeah.
Is that this one?
Yeah. Okay, that's good. All right. So, sorry for that little glitch. It worked on my computer, but when you get a new situation, it doesn't necessarily come across the way you want it to. Anyway, you have a process called tunneling where there's a barrier here made by this graph of potential versus distance, and if that barrier is there, quantum mechanically there's a small probability that the wave function doesn't just drop to zero like here, but it has a small tail out on the outside of the nucleus, and the alpha particle can escape. So what we're saying is if the depth of this potential well, which would correspond to the strength of the nuclear force, were to change, you can affect the rate of alpha decay. Okay. You can have a barrier penetration through there, okay? And if the strength were to change, you can change the number of nodes, which can drastically change. If this bend is here, but not over here, that can the graph on the right has one less node, and that can change the probability of escape. And you can have a jump. When one of these nodes changes, you can have a jump in the decay constant, or the decay probability shown here on the y-axis. You can have a sudden jump, and the decay probability changes drastically just from this small change in the strength of the nuclear force. And this is related to the decay probability, or in this case, the decay constant, which is the log of 2, or 0.693 divided by the half-life. And it's also the fraction of the nuclei decaying per unit time. Okay, so when you have a small change in the well depth, you can get this drastic jump in decay constant. Okay, and one of the projects that I had during rate was to use this boundary of the potential here that went up and also to the right a little bit, called it a diffuse boundary potential, and that we found by using Mathematica, we found that we could make the decay constant change by a factor of 10 million, just from a change in the number of nodes. Okay, so we know that nuclear force strengths could change for the most part, but we still have questions about how that would occur, what would be the exact way that would occur. You can always say God did it, and you're going to come back to that eventually anyway. You know, God is behind everything. He's the first cause of everything. But still, we'd like to know more about it. Okay. Another mechanism that I thought about with a student named Bruce Oliver was involving magnetic monopoles. Could they induce a nucleus to decay? And the answer is, we found definitely they could. Okay. Now, what are magnetic monopoles, and how would this happen? Okay. The magnetic monopoles surging out of the Earth's interior during the flood could induce the nucleus to transition to an excited state with a different spin and parity than the ground state, which then has a larger probability of decay. A magnetic monopole is an isolated north pole or a south pole. It could be either one. And it's not a dipole like this picture here, where there's both the north and the south end to the bar magnet. It's an isolated pole by itself, and this can exist according to theory, but how you get it is not quite what the sixth grader is going to think of. Sixth grader is going to think, well, I'll get my dad's coping saw and saw through the magnet, and that'll make a north pole over here and a south pole over here, right? And then you'll have a monopole, two monopoles, okay? But when you actually do that, that's not what happens. Okay, what happens is a new south pole forms right here. You get two dipoles instead of a monopole. You can't make a monopole in that way. It doesn't happen, okay? But theoretically, there could be these monopoles. A famous physicist named Dirac wrote some papers back in the 1930s proposing how this could happen. And the physicists take this seriously. They've looked for monopoles, for example, at the Large Hadron Collider, which is seen here in this aerial view over on the border between France and Switzerland. And actually, the border cuts right through this ring, the Large Hadron Collider. No, I'm sorry. This is Fermilab. This is not that. This is Fermilab near Chicago, okay, which is another previous accelerator, which is not quite as energetic as the Large Hadron Collider, but I'll get to the Large Hadron Collider in the next slide. But experiments at Fermilab rule out monopoles with a mass energy less than 600 giga-electron volts. Okay, and so it looks like the theory is in trouble. Now there's a new project with an acronym MOEDL, which is at the Large Hadron Collider, and they used the bigger accelerator to look for evidence for productions of pairs of monopoles, and they looked in the range of energies from 40 to, from masses up to 6 TeV, and a range of cross sections from 40 to 105 femtobarns, and they didn't find any existence. They didn't find any evidence. Okay, so do the monopoles exist? Well, there's no data as yet, no experimental data that indicates with confidence there are these things. But there's a good reason for that. Okay? I'll get to that on a slide after this one. This is a quote from a theoretical physicist named Joseph Polchinski, who lived until just last year, 2018. Okay? Wrote books on string theory and everything. Much more high-powered physicist than me. But here's a quote. He said, "But as I have discussed, the existence of magnetic monopoles seems like one of the safest bets that one can make about physics that hadn't been seen yet." Okay? So he thinks for sure they have to be there. Okay, and this was in a 2003 article in the International Journal of Modern Physics. Okay? Some high-powered physicists have looked at this question, and here's a snapshot of a paper by Rubikov, a Russian physicist from 1981, another one below it by a Nobel Prize winner from a paper of 1974. And from their studies of the theory, they find that the monopoles have to have extremely large masses. De Hoof said it had to be at least of the order of 137 times the mass of the so-called W particle, which is a particle that has been detected in experiments. Okay, and so that makes it 10 to the 11th GeV is the range where we would expect to find these particles. And so they're much more massive than we'd expect to be able to produce at the Large Hadron Collider. So that means that the experiments that have been done so far are worthless, okay, because you haven't got up to that energy. Okay, they may still exist. You haven't proven anything, okay? So could they be trapped inside the Earth? If they were produced out in space somewhere by some mechanism, could they be trapped inside the Earth? Well, the Earth has sort of a dipole. You could model it with a north end down here in the southern hemisphere and a south end up here, and that makes a magnetic field that exerts force on these monopoles, and it turns out there's a sort of an equilibrium point where monopoles would be trapped on either side of the core of the Earth. And in fact, in 1980, a physicist named Kerrigan proposed that monopoles could be trapped inside the Earth's core at a radius of 18% of the Earth's radius, and that's about where you'd expect to find them, down in there. So if you could get down in there, you might be able to do experiments with monopoles down there, but they're no use if they can't get to the surface, because we can't get down there. And so this might be a bubble graph, except that if there were magnetic field reversals during the Genesis flood, that would reverse the polarities and might send them out to the surface during the Genesis flood. Okay, so if the pole, if this north became south, south became north, then these monopoles would be forced out from their equilibrium positions. Okay, so now, could a magnetic monopole induce a nucleus to decay? It turns out the answer is definitely yes, it could. If they exist, if they're trapped in the Earth, that's two ifs. Okay, but definitely they could cause a nucleus to decay. Okay, the decay that's used in potassium-argon dating involves a potassium-40 nucleus, and it either decays to stable calcium-40 or to stable argon-40, and we measure the calcium and the argon, and that's how we get the date for the rock that you got this out of. But if you study the potassium nuclear energy levels, there's a series of levels as you go up in energy, and if a monopole were to come past these potassium nuclei, it would knock the nucleus into one of these excited states, for which the decay probability is completely different. And that, in other words, in effect, it would make it look like the decay was occurring more rapidly than normal when there are no monopoles around. So in other words, that's why I'm saying yes. Physicists have studied this question, and if the monopoles in enough quantity were to come past this rock, it would induce a lot of excitement to the excited states, and the prevalence of those excited states could make it look like there's a lot of decay occurring in a short amount of time, or accelerated decay. Okay, this has to get to the surface of the Earth, you have to have reversals in the Earth's magnetic field. Okay, so here on the right is a physicist of bygone days, Dr. Thomas Barnes, who was dean of the graduate school at Institute for Creation Research back in that day, and he wrote a book cover shown here, Origin and Destiny of the Earth's Magnetic Field. And he gathered data and showed that as you went down in time, starting from the 1800s, the Earth's dipole moment decreased. Okay, now on the left is shown Dr. Russell Humphreys, who added the thought that maybe these reversals in the magnetic field that we find in the data could have occurred during the Genesis flood. And also he made this graph shown here. Here's the dipole moment versus time. And when you plot this versus time, you see the Earth's field getting weaker and weaker. And Humphrey's idea was that the reversals, during a magnetic field reversal, the monopoles could be propelled to the surface. Well, that's my idea, but he's the one that thought of the reversals. And so this could maybe be a mechanism for accelerated decay. Okay? I'm going the wrong way. Okay. If you do the math, the magnetic monopoles can attain velocities about 100,000 centimeters per second, which is in the right range that they could escape the interior of the Earth during the reversals, but they're not going fast enough that they would cause permanent tracks in the rocks like fishing tracks. Okay, and if large numbers of magnetic monopoles were trapped inside the Earth, they can induce the decay of the potassium-40 nuclei, and other, like lead and uranium dating, could come to that category also. The monopoles must approach the nucleus within turns out about 10 to the minus 15 meters in order to be effective. But we do not know if this is what really happened or whether this is a correct mechanism. Okay, so that would be not a bulwark. It's a possible mechanism, okay, for accelerated decay, besides just saying the strength of the nuclear force changed. Okay. Another fact that you run into when you study nuclei is that nuclear pairing forces depend on the strength of the nuclear force. So for some nuclei, a slight change in nuclear force could cause a discontinuous change in the half-life. Okay, we know that nuclei like osmium-187 have a graph of pairing gap versus pairing strength shown here, and that if there were a slight change in the pairing strength along this axis, you would lose this phase of the nucleus where all the nuclei are paired up in pairs, and that would completely change the nucleus, which would completely change the half-life. Okay? For other nuclei, such as carbon-14, this is not the case. It turns out that when you figure out the same graph as you did for the osmium-187 and look at the real values of the pairing strength is over here to the left of this curve, and so there should be no pairing to begin with, and so a slight change in the nuclear force is not going to affect the carbon-14 like it would the osmium, and so we would not expect as much accelerated decay to occur, not even close to the same amount of accelerated decay for the carbon dating technique. Okay, so which could be a reason. I say could be. I didn't say it definitely is, but it could be a reason why carbon dating is not affected as much by the accelerated decay as potassium, argon, or some of the other methods. Okay, we know that the decays involved in radioactive dating involve forbidden transitions. And forbidden in this case means it can't ever happen. It just means that the transition between two states of a nucleus is allowed if certain selection rules for the changes in the quantum numbers are obeyed. Okay? And if the selection rules are not obeyed, it doesn't make the probability absolutely zero. It just makes it very small. Okay? So these transitions that are forbidden decays proceed only with a greatly reduced probability. Technically, the matrix element is very small. And so if the decay probability is very small, then the half-life is very large. And what kind of a decay do you need to do radioisotope dating of rocks? You need the ones where the half-life is very large. Okay? Not the ones where it's extremely small. So you're involving yourself with these forbidden transitions. by just what you're trying to do. Okay? So all these transitions that are used in radioisotope dating are what you call forbidden transitions. Okay? And these decays, these forbidden decays, are very sensitive to the energy released, this Greek letter delta right here that's in the formula. Okay? So a small change in the energy released in the decay can have a large effect on the decay rate. And so we know for certain that decay rates are very sensitive to energy releases. Okay? If you look at allowed decay, such as these in this top table, and forbidden decay, such as these in the bottom table, you find that for allowed transitions, the half-lives might be only a matter of seconds or hours, as shown here in these numbers here, 0.807 seconds for helium-6 decaying to lithium-6. So if the half-life is 0.807, you can't use that decay to date a rock because the decay is all over before you get the rock out of the field, right? Or actually before you ever got there, okay? And then the half-lives in the case of the forbidden transitions can be billions of years. That's shown in these tables. Like potassium argon is 1.27 times 10 to the 9th years. It's forbidden because there's a large change in nuclear spin. If it goes from 4 to 0, and that's a forbidden decay. Okay? And so there's a large change in spin. That's like the nucleus has to form this electron like it was way out at a large radius in order to carry off a lot of angular momentum. And that's not very likely. It doesn't mean that the probability is 0, but forming the mass way out here is not very likely. And so that's why the half-life is very small. Okay? And I think I'll skip some of the details on that slide. Okay? So when the parity changes, the electron and the antineutrino cannot be emitted without angular momentum being transferred. So the particles originate at an effective distance from the nuclear center, and that's what makes the probability small. Okay, and I think again I'm going to skip some of those details. Okay, but on the other hand, carbon-14 we don't think is well. We know that it's not a forbidden decay. The way you get carbon-14 is up in the upper atmosphere. Okay, there are nitrogen-14 atoms in the nitrogen molecules that are up there, and if a cosmic ray containing neutrons passes near this nitrogen-14, it can be absorbed, making carbon-14 by emission of a proton. Okay? And the carbon-14 dating method goes back to Libby in the 30s and 40s in his studies back then. And contrary to Libby's initial assumptions, the rate of production of carbon-14 in the upper atmosphere is not equal to its rate of removal by decay. Okay, we know the numbers are about 18.8 atoms per gram per minute versus 16.1 atoms per gram per minute. Those numbers aren't equal. So Libby originally wanted those to be equal. He thought they should be equal because after billions of years, they should be if the conditions on Earth stayed the same. But when they actually had the better measurements, they found they weren't equal. And so the original way that Libby wanted to do carbon-14 dating can't be done. Okay, you have to calibrate it in some way using tree rings or corals or some way of some external way of figuring a date for an artifact, a rock that you're going to use. Okay, and in carbon-14 dating, it's usually a piece of wood or something that was organic. Okay, but in the case of wood, you have these bristlecone pines that grow above 10,000 feet out in the White Mountains of California and other places nearby. Arizona, there's a few there, I believe. But you're assuming that there's one ring per year, and that as years go by, there's one ring formed per year, and that isn't necessarily true if the climate was different. Maybe there was a rainy season in May and then another rainy season in July, then you could get more than one ring formed in a year. And this is a actual bristlecone pine that I grew in my backyard, and you can see that there's a double ring out here, right in here. And so I think there are cases where you do get double rings. This is a very young tree. This is only 5 millimeters across here, but it's old enough to show the rings. And so I grew this in my backyard in 2 locations. I planted it in 1996 when I lived in Bluefield, Virginia. This is my sticker I had to pay for every year, scanned in so you could see it. And on the logo for Bluefield, Virginia, where I lived, it says, I don't know if you can read it there, it says Virginia's tallest town, because it's at 2,400 feet, and that's pretty big, pretty tall for a town, in Virginia anyway. Okay, not for Colorado, but all right. So it isn't 10,000 feet like in the White Mountains where the bristlecone pines grew, but I had these seeds, and I got some of them to grow. When I changed jobs, I decided they weren't going to respect my bristlecone pines in my backyard. It wasn't going to be my backyard anymore. So I transplanted it to my backyard in Simpsonville, where I live now. And the tree died in 2003, as you can see here. I'm not that good of a botanist, but in between I had this growing tree, and one of the biologists at Bob Jones took this picture for me, and you can see what happened there. Okay, okay. So anyway, you got to calibrate carbon-14. Now, another thing is about carbon-14 is the excited states are at very large energies. The first excited state of carbon-14 is at a whopping 6 MeVs above the ground state. Here it is up here on this scale. And the first excited state of nitrogen-14 is at 2.3 MeVs above the ground state. And so if these monopoles were to come out of the Earth and pass near the carbon-14s, they wouldn't be as effective in exciting them as they would be some other nuclei, because this energy gap is huge. Okay, so you couldn't get as many nuclei in excited states, and you couldn't cause what would be taken as accelerated decay. Okay, so carbon-14 is different than, say, the osmium case that I was mentioning a minute ago. We don't think there's pairing in the ground state of carbon-14, and also these energy levels are huge, which means if the monopoles are the reason for the accelerated decay, then they wouldn't be as likely. Okay, so no pairing gap exists for carbon-14, hence there is no pairing phase to destroy. Carbon-14 with its wide energy level spacing is not as sensitive to the strength of the nuclear force as the longer half-life nuclei. And I think that's something I'm pretty certain of. I'm not certain whether monopoles could do the accelerated decay or whether it's the strength of the nuclear force. I'm not as sure about that, but I am sure that carbon-14 is different. That's a bulwark in my opinion. Okay. All right, so back to the osmium. It has a different graph, and the pairing strength is thought to be up here in the region where there is a pairing gap, and so that's different. Okay, a small change in the nuclear force could affect osmium much more than carbon-14. Okay, the energy level spacing for the osmium is very small. 0.0098 MeV is the first excited state of osmium, 187. And the decay energy going from rhenium to osmium in the rhenium-osmium dating method is only 0.0026 MeVs. Okay, so a monopole coming by could affect this much more than it could for carbon-14. Okay, inside a star, you have high temperatures, and you'd have osmium nuclei excited to high energy levels, up in these energy levels, and so the osmium 187 at the temperature of a star would have appreciable populations of atoms in these excited states, and you would get accelerated decay. And this is known by the astronomical community, and we discovered this 20, 30 years ago, and this is a known fact. Okay, now I want to switch to a different mechanism that could cause accelerated decay, a nearby supernova, okay? I published a paper in the Creationist Society Quarterly in 2017 where I outlined what I think about this, and I've been studying it since. I'm going to add some new things here in a minute, but here's one of the things I said in that 2017 paper, okay? Uranium-238 is one of the parent nuclei that we use in radioisotope dating, uranium-lead dating. Uranium eventually, after several stages of decay, ends up as lead. But in the early stages, the most probable decay is to an alpha decay, which makes thorium-234. So you decrease the number of neutrons by 2, you decrease the number of protons by 2. That takes it from 92 protons to 90, which changes you from uranium to thorium. And 2 and 2 is 4. You change from 238 minus 4 to 234. So alpha decay of the 238 would make 234, and that's the normal way that uranium decays in our world today. If we take the uranium-238 to the lab, we find alpha particles coming out, and not much beta decay. Okay, but if this could be changed in some way by a change in the strength of the weak nuclear force or something like that, you could have a change in the mass of U-238, which would make it bigger than the mass of the daughter Neptunium-238 rather than smaller. Okay, a current measured value of the Neptunium-238, this nucleus up here, that nucleus has a mass of 238.05094 atomic mass units. Okay, and the U-238 is slightly smaller than that, 238.0507075 is slightly smaller, right? And so beta decay of U-238 is impossible because you'd have to create energy to make the Neptunium-238. But if during this episode you could make this mass smaller and that one bigger, it could be switched around, and then you could have a lot of decay occur in a short time where the uranium was going through beta decay rather than alpha decay. And the question is, could that happen? And I think there is a mechanism where that could happen. If there were a nearby supernova and there were a change in the hypothetical acceleron field, the changes in the mass of the U-238 could occur. Okay? And, all right, before I get into that in more detail, I want to mention the speed of light. Okay? Back when I was young and foolish, I'm still old and foolish, but anyway, back then, in 1992, this is a snapshot of a paper I published in the Creationist Society Quarterly, a determination of the speed of light in the 17th century. Okay? And this says, the abstract, a careful computer analysis of data taken primarily by Romer in the 1670s is performed to determine the speed of light at that date. Blah, blah, blah. Okay. The upshot of my work was that I didn't find the speed of light be appreciably different. It was within 0.4% 300 years ago in 1670s as it is today. Okay? And this passed peer review, so there are at least 2 physicists who agreed that this was a valid study. And I don't know anybody with a degree in physics who has told me this is wrong. Okay? Now, there is a Canadian guy with a degree in statistics who thinks this has to be wrong. He can't tell me why it's wrong, but he thinks it has to be wrong. And I haven't seen him in several years. I think he still thinks that. But anyway, but when he did his statistics study, he was using positions of Jupiter which hadn't been corrected for the effects of Saturn, the perturbations of Jupiter's orbit caused by Saturn, which I included in this paper. Okay, and so I think his study is flawed for that reason. He's never been able to give me a reason why my study is flawed. Just he said it has to be wrong because the speed of light changed. Okay, and so I'm the bad guy in this case. I'm the guy that came along and told the guys who were going before me that nope, the data don't show that. Okay, the speed of light in 300 years ago was within 0.4% of what it is now. Okay, so okay, but now there's a physicist. He's of Portuguese extraction, João Magalhães. I'm not sure I even pronounced that right. I'm not even close, probably, but it's Portuguese, and you can excuse me for that reason. How many of you guys speak Portuguese? You know, I used to have a guy in the office next to me who did, but anyway, he published a book called "Faster Than the Speed of Light." Okay, he had a fellowship in Cambridge, England, and was allowed to study this subject for several years. And after that study, he published this book, and his idea is that the speed of light changed early in the history of the universe. He doesn't think it was different 300 years ago. So fortunately for me, this high-powered physicist didn't agree with my paper. He just thinks it happened early in the history of the universe. Okay, and my study actually said that in the 1670s the speed of light was within 0.4% of what it is now. Okay, so if I'm right, that doesn't disprove that it could have been 0.1% different. My data only showed it was within 0.4% of the current value. And my study doesn't say anything about the time of Christ or at the time of the Genesis flood, because this is just studying data from 1670s. Okay? If you can give me some data of these eclipses of Jupiter from time of Christ, then I could do this for then, but nobody recorded any data from that, or any physicists doing that back then. Okay, no astronomers doing that back then. Okay, so I cannot contradict what he's saying here, that this speed of light might have been different. Okay, that's an uncertainty. Okay, you can watch on Netflix a program. You could use the search buttons that you have on Netflix. Search for Einstein's biggest blunder. If it isn't already on your feed, mine, I just saw that there one afternoon when I was bored, and I decided to watch it. And it features this Portuguese guy named Magalhães, among others, astronomers and physicists. And it's a very interesting Netflix thing. If you're bored some afternoon, like I was, go ahead. I recommend it. Okay, but Einstein's biggest blunder. But anyway, that's an uncertainty. Was the speed of light different? We don't know. Okay, but I'll go back to my acceleron field and all that. Okay, supernova and all that. Okay, this is a picture of the remnant of the Crab Nebula, which we think exploded in 1054 AD. Okay, and these are the gas and dust clouds that are going out from it. It's called the Crab Nebula because an astronomer thought this looked like a crab. No pinchers on it, just the shape of the crab's body. Okay, it's not in the constellation. There's a constellation called the Crab. It's actually in the Taurus the Bull constellation up over here. M1 is the designation for it. Messier's list number 1. Okay, and north of Orion, over in there. Okay, and what I'm proposing in this is that when the supernova exploded, it sent out a pulse in this acceleron field that eventually reaches Earth and causes a change in the mass of uranium-238, which leads to the decay to the neptunium instead of the alpha emission, and could cause accelerated decay. Okay. In a supernova, here's the sequence of events. The star begins collapsing into itself when it runs out of nuclear fuel. Okay, that's simplified from what the computer simulations show. That's just a simplified description of it. Okay, then energy can leave the star by a profuse emission of neutrinos. So it loses all this energy because the neutrinos can get out where other particles can't. Okay, so that's like pulling the rug out underneath somebody. Now you don't have this energy anymore, and the imbalance causes the star to blow itself apart. It collapses in and rebounds. Stuff goes everywhere. Okay, even for relatively nearby stars, it takes years for the blast to reach planet Earth. Okay, so what was ordained to happen years ago will eventually reach Earth. We don't know it yet, but God knows, and it's on its way. It's just like in the days of Noah, they were marrying and giving in marriage, and they didn't know that tomorrow wouldn't be the same. Okay, it's ordained to happen. It's going to happen. We don't know when, but it's coming. Okay, here's another remnant. the Vela Nebula, which is also a supernova remnant, but it's closer to Earth. It's only 800 light years away. Okay, and this is a southern constellation Vela the Sail. I don't know if the room's dark enough you can see that, but this is the Vela right here, and you have to live in the southern hemisphere to see that. Maybe South Florida or something, but not here. Okay, this is another picture of the supernova remnant for Vela and its surroundings, and there's a pulsar actually discovered right there. A pulsar is a star that sends out radio emissions with a very rapid, regular emission rate. So you can measure the frequency very precisely, okay, pulsar. And that's what many of these neutron stars change into those, okay? And if conditions are right, you can detect that pulsar at planet Earth, okay? So the neutrino is a special particle. It was proposed by this guy shown here, Wolfgang Pauli, who is a high-powered physicist of the 1930s and on. He's passed away now, but he was the guy who proposed neutrinos back in the 30s. They have no electric charge. They travel near the speed of light. They have a very small rest mass, and they were proposed to conserve energy and spin in beta decays. Okay, and there are 3 known flavors. Today we probably didn't know this, but now we know there's electron, muon, and tau neutrinos. Okay, this is the Rhine River right here, and this thing right here is called a spectrometer. These are barges here, so that's a big thing. And here it is coming through the streets of this village called Leopoldshafen, north of Karlsruhe, Germany. And actually, I lived in this town, not here on this street, but a couple of blocks over. Back in 75 and 76, I had a postdoc, and this is where I lived. But after I was there, they brought this thing through the streets. I guess, I don't know how the mayor and everybody else gave them permission, but anyway, they did, okay? And it went to the Nuclear Research Center where they set it up. Okay, it was made elsewhere in Germany, brought down 2 rivers, and landed here on the Rhine River near Leopoldshafen, okay? And this is where they put it over here, where that yellow dot is. And actually, I worked in one of these buildings for those 2 years. And it's mainly based on, this spectrometer is based on tritium decay. Tritium is the isotope of hydrogen that has 2 neutrons besides just a proton, okay? And then it undergoes beta decay, and in 3 or 4 years from now, they'll probably have a value for the neutrino mass. If the neutrino mass is between 2 electron volts and 0.2 electron volts, this spectrometer will be sensitive enough to find that mass, and they'll have a value. They have to take data for a long time, though, to get it, see, and they have maintenance periods, so it's unpredictable when they're going to get that. But if it's in that range, they're going to measure it. If it's not, if it's smaller than that, we think there's a lower limit. It has to be, the neutrino mass has to be at least 0.05 electron volts, okay? So if it's less than 0.2 and more than 0.05, that's a pretty narrow range, but it could be in there also, and then this spectrometer will just put a new upper limit on it. But they're trying to measure that neutrino mass, okay? Recent physics literature contains theories in which the neutrino mass is coupled to the neutrino density. That is, more neutrinos per unit volume makes a different neutrino mass. Okay, and this is because of the so-called acceleron field, shown here in color. Okay, acceleron field. Okay, this acceleron field is hypothesized to resemble the Higgs field. We know there is a Higgs field now, because the discovery in 2012 of the Large Hadron Collider. But this would be a hypothetical field that's similar but not the same as the Higgs field, and it would change strength due to neutrino couplings and variation in neutrino density. So if a supernova were to send large numbers of neutrinos towards Earth, there could be a change in this acceleron field which would arrive here at Earth and could affect nuclei like U-238, okay? Now, a scalar particle like the Higgs has a decay probability that depends on its mass. This is a graph showing the branching ratios on the vertical axis and versus the Higgs mass. We actually narrowed down the Higgs mass. It's about 125 giga electron volts, so you should go vertically from this point to get the values for decay into a bottom quark and an anti-bottom quark on this branch, or between a Z particle, 2 Z particles on this branch. But you can calculate from these Feynman diagrams, you can calculate the decays to the different types of particles, and the result depends on the mass. Okay, back in the 70s, they thought the Higgs mass could be on the order of electron volts. Now it's known to be 125 giga electron volts. Okay, it kept going up until they finally nailed it at the Large Hadron Collider. Okay, but the acceleron has an unknown mass. It could be very small. It could be in the range of electron volts, contrary to what the Higgs is. And then the decay probability, if it's a small mass like that, it can only decay into either 2 photons or to a neutrino and an antineutrino. And these are the Feynman diagrams that go with this. And it turns out that a scalar particle cannot decay directly into 2 photons. It has to have this triangle diagram in between. Here's a quote from a book called The Most Wanted Particle, which came out in 2015. It said, since the photon's mass is 0, the Higgs really ought not to decay into photons at all. It does not directly. It has to go through a loop of some other particle like these electrons here. Okay, and so, but that probability is non-zero, and we can calculate that. And it turns out that if the acceleron mass is in the range of 20 to 100 electron volts, then using the Feynman rules, which I've done, I got out my notes, like I described, I got out my notes from graduate school and tried to remember that again. And I had help from some results in the papers in the physics literature. If the masses of the acceleron are in the range 20 to 100 electron volts, it turns out that the lifetimes for the acceleron would be in the 10 to 1,000 year range. So here's the picture. This burst in the acceleron field gets to Earth as a result of a foreordained explosion. It gets to Earth right at the time of the Genesis flood. So it affects these nuclei at that time, but it also, the acceleron field decays away on a scale of 10 to 1,000 years, so it would be accelerated decay tapering off after the flood. And by today, it isn't occurring anymore. Okay? And the photon burst from a supernova explosion is gone in a year or so, except for some reflections off of clouds that may be out there, but it's gone. And but if the half-life of the acceleron is in this range, this could be a viable mechanism for accelerated decay. Okay, so that's uncertain, but I'm sure it could be if this unknown particle. We do not know for sure that the acceleron field exists. Let me say that. Okay, if that's the case, then I've been foolish in talking about this even. But I've been foolish for other reasons, so I'm really willing to do that. Okay, but if it does exist, we do not know if it has a mass in that range, 10 to 200 electron volts. Okay. However, it remains a possibility at present. Okay, so that's another possible mechanism for accelerated decay. This shows a paper by Firestone from 2014 in which he showed the excess carbon-14 versus dates, and he came up with his graph. But after I did my 2017 paper, I discovered that there was a paper in another journal. He didn't publish the criticism in the same journal. This other paper by Malot et al. In 2015, only a year after the original paper, this other paper was in International Journal of Astrobiology. Okay, and the first paper was in Firestone was in Astrophysical Journal. So why was the criticism a different journal? I don't know, but it was. And I didn't discover it until after my 2017 paper, which is poor scholarship on my part, but I'll admit it. Okay, but anyway, this paper criticized Firestone's use of the data. In other words, they said this graph isn't exactly right. But even that paper said that there had to be a lot of supernova in our immediate neighborhood in the recent past. Okay, so nobody's denying that there's been supernova in our neighborhood in the recent past, and So it remains a viable mechanism, that one, okay? And so I'm not sure that occurred, but it's a possibility. And I'm done. Yeah. Questions? Switch is on the bottom, I think. Oh.
Okay, so magnetic monopoles, they could affect both alpha and beta decay,
Yeah.
and
They could excite either type of nucleus to an excited state where the probability of alpha or beta decay could occur. Could be different, would be different.
yeah.
For those who, I wrote down a couple of questions just really quickly. If you could, what is an alpha particle and what is a beta particle? I know, but other people may not know that. So,
Okay.
And I'll give it back to you.
Okay, an alpha particle is the nucleus of a helium atom, or the normal form of helium. There's helium-5 and other things, but helium has 2 neutrons and 2 protons in the nucleus. As you strip away the electrons, that's an alpha particle. And the nucleus, some nuclei have a propensity for emitting alpha particles. Okay, why don't they emit oxygen nuclei? Or, well, it turns out in some experiments they do, but that probably is so small that it doesn't affect radioisotope dating. So an alpha particle is 2 neutrons and 2 protons stuck together. Okay, in beta decay you get an electron, in beta minus decay, you get an electron and an antineutrino come out. We're not really sure that antineutrinos are different from neutrinos. That's something for experiments going to have to decide. It's looking now like there is no double beta decay, so antineutrino and neutrino are different, but it hasn't totally been decided yet. But if a neutron changes into a proton, it can emit an electron and an antineutrino in that process of changing from a neutron to a proton, and that's a beta decay. That's a beta minus decay. I won't talk about beta plus because that's just complicated, I think. But yeah. Okay.
Well, I'm just trying to clarify, make sure I got what you were saying straight. So it can affect both alpha and beta decay,
Yeah.
but certain types of beta decay, it's gonna affect less, like carbon-14.
Yes.
Okay. And so some physicists apparently thought that magnetic monopoles would have a very large mass, much larger than we could detect at this point in time, right?
Yeah. In the literature, you'll find papers where they found a track and they thought they'd found a monopole, and this is reported by an Italian physicist, but nobody else could repeat that. So it's for the Journal of Irreproducible Results. We can't do it again, so that means nobody believes the first report.
Okay.
But if there were a large enough flux of monopoles that we could detect them in cloud chambers or emulsions or whatever, in the electronic detectors that they use at the Large Hadron Collider, we would have evidence, but we don't. And
So was the collider trying to make a monopole,
they
or was
were
it trying to?
This project that was at the Large Hadron Collider was assuming that the monopole was lighter than the theorists thought it should be, and so they were going to look for it anyway, even though the theorists didn't think they'd find it, and so they didn't find it. So the theorists are,
But they were actually trying
plus,
to.
they don't think it should have found it anyway. But
They were actually trying to create one.
yeah, from the high energy collisions at the
Right.
at the collider.
So if monopoles do exist and they are much more massive than the colliders are able to detect at this time,
Yeah.
or create at this time, I mean, is it conceivable that there are colliders in the near future that could
Yeah.
reach those energies?
They're talking about a linear collider being the next one, either in Japan or China or maybe Europe, and it's iffy because it's like you remember the superconducting super collider that was supposed to be built in Texas, the big ring, and they initially approved it. But when it wasn't in my district anymore, I didn't vote for it anymore. So that's what that might happen to that too. But they proposed bigger colliders, and but they may need one as big as the solar system to do that. And that's obviously not going to happen in our lifetime. But
should know, what energies they're able to achieve.
yeah.
So is this next generation, should it be able to do that?
I don't think so. Not that much, unless the monopol's less massive than they think.
Gene, I wasn't able to follow how these acceleron particles that are associated with the acceleron field, if I understood correctly, are created by a flux of neutrinos. Can you repeat what you said?
Yeah. Okay. So they're a scalar particle. That means a particle that doesn't have a direction in space. The acceleron particles. They're like the Higgs. They have no... an electric field has a direction in space. Okay? Like if you have two metal plates, one's positive and one's negative, and the electric field points from the positive plate to the negative plate. But an acceleron field wouldn't have a direction it points, not up, down, or wherever. Okay? It's a scalar particle. And it's like the Higgs. The Higgs field we think is non-zero in empty space, but it doesn't have a direction it points in, and it causes a mass for some other types of particles, not for everything. Okay. There was a blasphemous book written several years ago, "The God Particle." You may have heard of that, and that was before the Higgs particle was discovered. Okay, you shouldn't call it a God particle. And a lot of physicists, even the atheist physicists, don't like the title of that was given to that book. I think it was the publisher actually wanted to do that rather than the physicist. But anyway, because it would sell more books if it was blasphemous. That's what they thought. And maybe it did. I don't know. But getting back to your question, the Higgs field, if it's non-zero, is going to produce Higgs particles all the time. And then these Higgs particles are gone in a million billionths of a second. They have a very short lifetime. Okay, and that's because you had these different decay modes which are possible for a heavy particle at 125 giga-electron volts that aren't possible for the acceleron particle if it's much lighter in mass. So if there were an acceleron field that's non-zero in space, in other words, there's a pulse in this acceleron field that gets here, it would affect the neutrinos. We think the theory that proposed this acceleron particle said that the density of neutrinos affects the acceleron for the same reason that the Higgs interacts with quarks or whatever else it interacts with.
Okay, so I'm trying to understand the logical connection with a nearby supernova that emits a flood of neutrinos and the appearance of this acceleron field.
Right.
How does...
well, if there are electrons around, then you have electric fields, right?
Yes.
Okay. And at the quantum level, that means there's photons. If there's electrons and positrons around, you get photons. Okay? Same reason. If there are neutrinos around, you have acceleron field, if it does exist and couples in this way.
Yeah, but the presumably these neutrinos are only it's like a pulse or a wave of these neutrinos from the supernova that just pass through the Earth and last only a brief period of time. That they're
yes, that's exactly right.
And so,
but if the acceleron on a conventional time scale, the acceleron decaying in 10 to 1,000 years, that's a pulse too. But for the flood scale, that might. What I'm saying is, if the acceleron mass is in this range, 20 to 100 electron volts, then using the Feynman rule shows that the decay rate of the acceleron is 10 to 1,000 years. So the neutrino pulse may be gone, but the acceleron field is not going to go away that rapidly.
okay, so I was trying to understand that this wave or this front of neutrinos leaves behind an acceleron field, even though that front of traveling, that pulse of neutrinos is long gone, the acceleron field that they generate at a given place persists. Is that what you're saying?
Yeah, because the particle half-life is not as
Okay.
short as that
All right, I'm
pulse.
just trying to make sure that's. I thought
And so it would still affect the nuclei for, the influence would go down over time if this is the correct half-life, but it would still be affecting them.
Okay. All right, I just wanted to try to make sure I was tracking with you on that.
Yes, sir.
I have a question.
Okay.
Again, for an issue of clarification for people, and I'm not going to try to explain this. I'll let you do it. I noticed that when you were talking about mass, it was measured in terms of electron volts, in terms of energy. Let me just ask: is that because of E equals mc squared, that
Yes.
Einstein's relation that we talk about?
Yeah, it's common.
So it's E over c squared.
It's common if you go to the Large Hadron Collider, they're going to do just what I did. They're not going to try to explain that. E equals mc squared. So where was that uranium graph? Yeah. If you measure atomic mass in atomic mass units, which is 1/12 the mass of a carbon-12 atom, then the mass of the uranium is 238. Then you have E equals mc squared. So to get to energy units, and if E equals mc squared, then it doesn't matter whether you use energy units or mass units.
But in high particle physics, they use energy units, right?
Yeah.
That's why you're talking about 120 GeV, 120 billion electron volts.
Yeah.
It's because of it's so large because of C. It's the C squared.
Yes.
Again, I want to return to the question about the acceleron field, and I never heard of it before. Is it that the supernova produces? They think it produces an acceleron field, and neutrinos are the neutrinos flux produce the acceleron field?
Okay,
The two effects of the
so
supernova.
When I was taking my first physics course in college, I had a physics in high school, but when I got to my first physics course in college, I remember very clearly my physics teacher standing in front of the auditorium. It was like 100 students, I think, and he told us that it would take 1 million light years of solid lead to stop half of the beam of neutrinos. And the way he said it made us all laugh. If you say it right, maybe not the way I just said it, but we laughed, because at Oklahoma State you thought about football too, and you wanted him for your wide receiver or something, But all these nuclear reactions inside the star can only occur to a point when you build up. When you try to get past the iron region of the chart of nuclei, it doesn't work anymore because you have to absorb energy instead of emitting it when you merge nuclei. And so the star runs out of nuclear fuel at a certain point, and then all these beta decays produce tremendous amounts of neutrinos, and since they can pass through 1 million light years of solid lead, then they can get out of the star. Okay, at some point. Now, the star is very dense, so that isn't exactly true inside the star, in some parts of the star, in the dense core. But during the explosion, they get out, and they get out through all this mass. And if there is an acceleron field, which is not certain, I admit that, okay, then, and it couples to the neutrinos, the acceleron field is going to be formed when this big density of neutrinos comes out, and it'll be part of the pulse that heads towards planet Earth. And if this pulse gets here at the time of the Genesis flood, it might be the culprit that I'm looking for, for causing some of these effects,
Did you? I saw something that you also thought that perhaps the neutrino flux could carry away the heat that was generated by the.
Yeah, it carries off energy, and this energy gets out of the star without bouncing around against other atoms. It just zooms past, like this wingback that run through all the other players, without getting touched, and it carries off the energy. The star doesn't have it anymore. It doesn't have the heat to hold up the upper layers, so they collapse in and bounce back and blow everything into the surroundings. And
How would the neutrino flux carry away the heat that was generated on
They
the
have
Earth,
kinetic energy.
on the Earth?
pardon me?
On the Earth, by the genesis, I mean the
Okay.
accelerated
I'm
decay.
not saying that the neutrinos directly cause the accelerated decay. I'm saying it's this acceleron field, and that could affect the uranium mass. And if the uranium mass were changed only slightly, it could change it from less than the mass of Neptunium to greater, and then you start having beta decay occurring very rapidly, and instead of the alpha decay, and which takes has a very long half-life, and you wouldn't have this slow rate of decay that normally predominates.
And so that you wouldn't have the heat problem in. I know one of the issues of the rate research is that
Yeah.
it generates a tremendous amount of heat, probably
Yeah.
enough to vaporize the Earth or something like that. It was a lot of heat, and I thought that you had postulated something about the neutrino flux carrying that heat away from the Earth somehow.
Oh,
Or am I mistaken?
well, these neutrinos would carry off some energy, and that might make the heat problem smaller. I don't think it would completely solve it, but it might make it more manageable. If
Okay.
the uranium, yeah.
I want to get back to the monopole issue,
Okay.
and can you? We're talking about converting from mass units to energy units, and you're quoting the mass of these monopoles in terms of energy units. Can you translate? I haven't done that in my head. But how much mass would a single monopole have in terms of grams? It's pretty big, isn't it?
Yeah, I think it's a fraction of a gram,
Okay.
0.1 or something, if I remember right. I haven't looked at that recently. But
And
I'm used to thinking of these other units, but not that. But I've seen it. Somebody calculated that out, and
so we're talking about these particles that weigh, at least a fraction of a gram. That's a pretty massive compared with the size of a proton or neutron. That's huge.
yeah.
And
So if it passed near, it's going to shake things up. It's going to.
yeah, I would think it would produce all kinds of tracks and damage in rocks.
Yeah. Well, in my 2017 paper, you find, where did I put that? That's not it. Where is it? Yeah. I took these numbers out of my paper, and Bruce Oliver and I had figured out how much energy it takes to make a track. And for a speed of about that much, we figured you wouldn't get a track, like you wouldn't get a fishing track.
Okay, so again, I don't have much. I've never worked with any particle like this before, as far as how it
I mean,
affects
it is a
matter.
huge mass, but what it does depends on the speed also. Okay, and fission tracks during nuclear fission, the two fragments accelerate away from each other at over 1/10 the speed of light. I said that when I worked at Naval Nuclear Power School, and there was this other guy who disagreed. No, I couldn't. It's not that fast. But I had calculated, and he hadn't, and he was just blowing, and I knew that was. I had calculated. Okay, the two fragments accelerated at over 1/10 the speed of light, and they're huge, massive particles, and they do produce trails of damage that Andrew Snelling took to the lab, and he took pictures of these.
Well, 10 to the 5th centimeters per second. That's a kilometer per second. That's the speed of a rifle bullet.
Yeah.
So you
But
have.
it's not. But the speed of light is.
I know, but I'm just thinking about a particle that is a fraction of a gram traveling the speed of a rifle
Figure out
bullet.
the energy. What you need is the energy, and you figure out the energy and how much energy it takes to make a track, and This is too
Okay.
small.
So you're having a lot of these. That hypothesis envisions vast numbers of these that I don't know how many atoms it could trigger accelerated decay in a single one of these particles. Presumably, quite a few. But I'm just trying to.
Yeah, it could be quite, because as it goes by, it doesn't lose all its energy in one collision. It's going to make a trail of excited atoms. But that doesn't mean that you've knocked the atoms away from this region and produces a void, which is what a fission track was, the way it started, and
All right,
before the etching, But
So the basic, as far as the effect of a monopole on ordinary matter, you're saying that there's a very small cross section, if you will, or that kind of particle can pass through a lot of matter without affecting it very much.
at that it depends on the speed. But at this speed, we did the numbers, and I don't have them with me, but where's that thing? At this speed, 10 to the 5th centimeters per second, we ran the numbers and no tracks,
Okay.
not enough energy.
And
But then it could accelerate. It could cause have enough energy to make the protons, or make the nucleus assume a new state with a different spin by exciting the neutrons or protons.
Okay. All right. I'm just trying to get a little better feel for how these
I didn't
monopoles-
run the numbers yesterday, so I'm sorry I can't put all the details up here. But and I didn't know that question was coming. But we did run the numbers back then when I did that 2017 paper, and I could look it up for you if you
All
want.
right. And another issue is how does the Earth's magnetic field, how is it so effective in trapping these monopoles? The Earth's magnetic field is modest, depending on. It's not an extreme field like you would have, in a neutron star or probably even in the sun. It's a fraction of a Gauss or something like that.
But it's larger at depth than it is at the surface, which is still not that big. But
I don't think it changes that much down. Yeah, I guess it is less at the surface, yes. But what you're saying is that even at those is what to me would seem modest, a modest electron.
But if the monopole has
field.
lost energy after it's traveled through space or wherever it came from, if it's lost its energy, even a small force is going to move it.
Okay.
And they could get. I didn't make this up, this other physicist who isn't a creationist, I don't think, Kerrigan, 1980. I think he had an article in Scientific American, and he thought they could be trapped inside the Earth.
Okay. So in general, my grasp is of the magnetic field inside the outer core. A colleague of mine, Gary Glatzmeyer, was the first to model claim to model the dynamo, a core dynamo, and his numerical calculations showed all the magnetic field lines. So there is a lot of if that model is even roughly correct, and I assume that's what this guy would be drawing upon. There is a lot of spatial variation in the magnetic field inside the outer core.
Yeah. But Kerrigan wasn't talking about sending the monopoles out during field reversal. He didn't talk about that. That was my foolish invention, But
Okay,
and
so
it might
you're-
be a foolish invention.
all right. So
time will
you're
tell, yeah.
okay. So I'm just trying to understand how these, what the field configuration is that causes a trapping of these.
See, it's an isolated pole, And any magnetic field at all is going to cause a force, and just like a charged particle is affected by an electric field. You put a charged particle between a positive metal plate and a negative metal plate. If it's a positive particle, it goes towards the negative plate. And then, does it take 3 seconds or 3/10 of a second? Well, I don't know. You have to put the numbers. But the monopole, when you put it in this Earth's magnetic field, it's going to go along the field lines, and there comes a point where the forces balance out and it just stays there. So that theoretically that point is at 0.18 times the radius of the Earth, the calculation showed.
Yeah, so do these,
In other words, the gravity of the Earth balances out the magnetic force at these points, one for the one polarity over here and the other for the other polarity over there.
all right, so I think you're maybe giving me what I'm looking for, what causes a balance. You're saying it's a balance of gravity acting on this
Yeah.
on this particle and against the magnetic force
Yeah.
of the field. So somehow
Yeah. So I didn't make up the 0.18. I think I got that out of Kerrigan, but we had checked it to make sure we thought that was
okay.
the right order of magnitude.
So I can imagine if there is a field reversal, then the particle is going to want to go in the opposite direction and
Yeah.
might have enough energy to escape.
Yeah, that's the idea. Yeah.
Okay.
And if Glatzmeyer's simulations are any indication, there's going to be stuff like that. It's going to send some amount. Yeah.
Well, much of what you're saying is well over my head, but I've learned a lot. I have a question about monopoles.
Yeah.
I understand you can have positive charge without negative charge and negative charge without positive charge.
Mhm.
But I don't get how you can have north without south. So is a monopole, I'm imagining if you zoomed way up on it, it might look like a sphere, and the outside surface of the sphere is maybe north, and the center of the sphere is south. Is that what we're talking about? Like a magnet's inverted on itself? So you see north when you're looking at it, but if you drilled into the center, there'd be a south in the center of
It'd be
the...
like this picture here,
Yeah.
where if this is the North Pole, then the field lines point out
Yep.
from the pole, or if you want to draw it as a rectangle, then if it's the South Pole, they all point in, or they all point out if it's the North
Okay. But is there another pole somewhere, like buried inside it? Or...
Pole. No, it's just this can travel through space by itself, in theory.
All right. So I get electrons, negative charge. There's a
Like we were
particle
saying, if you
there.
go to the lab with
Yeah.
a coping saw, you can't do this.
Yeah, I know.
Okay. Yeah.
So what you got, that north monopole would be attracted to the south pole of the bar magnet.
Yeah, if there's a bar magnet around, it would be attracted to it. Yes, it'd be repelled by the North Pole and attracted to the South Pole, and it moves along the direction of the field lines. Okay, so these field lines go in at the South Pole and they go out at the North Pole.
So if that were inside the Earth, it would be attracted. So if that type of monopole were inside the Earth, it'd be attracted toward the south magnetic pole of the Earth.
Yeah, but
and-
actually, see, the Earth's South Pole is in the northern hemisphere.
Yeah, you said that, yeah. But it would tend to be attracted there along the field line.
Yeah.
But you're saying that when it gets up, in this case in the northern hemisphere, and tries to move, it's going to be let's see. No,
The
it's-
gravity force is in, so whichever side it's in equilibrium, it has to be where the force is outward.
Okay, so what you're saying is that if it's near the south magnetic, let's see, near the north, well,
Let's just say it this way: there is a side on which it bounces, and the other side it doesn't.
Okay.
You have to have the opposite polarity.
okay.
Yeah.
It seems like that balance might be rather tenuous, but okay, all right, that helps a lot.
Well, what you're talking about is unstable equilibrium. Move it out a little bit, would it fly off? No, because then one force is bigger than the other and pulls it back. I think it is stable equilibrium.
Okay.
Yeah. As long as the field lines are behaving themselves, not doing what what your friend was saying.
Rob, do you have any more questions? Okay. I think this was just an amazing display of erudition oh, I just wanted to ask you. I do have one more question, and that is, of all the various different scenarios for accelerated decay, which one do you think is most likely to happen? Or did the Lord just say, I'm going to change that constant, I'm the creator, I can do that, and then cause accelerated decay, and then shut that phenomenon off after the flood?
My job as a creation scientist, creation part means I respect the scriptures, and if my hypothesis doesn't agree with the scriptures, I stop working on that line. Whereas, so my job as a scientist is to formulate hypotheses that have no contradiction with things we know, and then put them out there to see if somebody can, if John or Rob or you yourself could find a reason it doesn't work. And then if I find a convincing reason it doesn't work, then I throw it away. And so, what have I got here? I've got small changes in the nuclear force.
Move towards the mic. So.
Okay, I got small changes in the nuclear force. I got monopoles escaping during reversals of the magnetic field during the flood. And then I talked about pairing phases of nuclei, but that's really probably dealing with this changes in the strength of the nuclear force. Then I talked about this accelerated acceleron field. So that would be there's really only 3 hypotheses I've given you here. Okay, and I don't know which one's correct. The change in the strength of the nuclear force, that could be correct because God could have done that. Okay, end of story. If he did that, okay, good. But I like the ones where you can say this happened 1,000 years ago and just now got to Earth because that's foreordained, and I like that because then I can work on something. If God just did it by changing the strength of the forces, then I can only study the effects of that, not try to give a mechanism. You see what I'm saying?
Yes.
Yeah.
Yes.
And so I don't know that I have a favorite here. The one I'm working on now is the acceleron field, and so emotionally I wouldn't like it if that was suddenly proven wrong, but if it was, then I'd have to do something else.
And there are other physicists that are working on these possibilities.
So I didn't propose the acceleron field.
Okay.
It was a group, Fardon, Fardon, and others who proposed this, and I don't think they're doing much on it right now. It was in the 2000s, and they put this out in the literature, and I don't think they're doing much on it right now. And amongst creationists, I don't know any other creationists working on this.
No, I don't know either. And what about are physicists working on the monopole?
Yeah. There's whole teams working at Large Hadron Collider. The Hadron Collider is shut down now for upgrade to the full design energy. Okay, so I assume this project would go on at the full design energy once they start up again in a year or two.
Okay.
Yeah.
Okay.
Yeah.
Well, thank you very much, Dean. Is there any other? Anybody else want to ask a question? All righty. Well, then we want to dismiss for lunch, right? So, and we will resume at 2:00 for geophysics with Dr. John Baumgartner. See you then. Pardon me? It says 1:30. See, 2 to 3. No, it's actually 2. It's 2. I think it is. Well, let's check the website. Hold on. I thought it was 3:30, 4:30, 3:02. I think it is 2, but yeah. Let me check the website here. Okay, let me, let's see.
Out in dead space, space where there's no magnetic pulse from light.
It says 130?
The speed of light speeds up.
Wait a minute, let me see, I don't see how that could be, but I guess maybe it is.
I would think more of over time rather than out in space, but
Oh, wait a minute here.
in the
Just a minute.
early 2000s, there was a group that thought they'd, that thought
Let's get the
they'd
time here
had
correct.
evidence for a change in the fine structure constant, which could also mean a change in speed of light. Another group later on contradicted them. They didn't find that. And then the first group said, well, maybe it's you're in a different
Yeah,
direction
that's the
than we are,
130.
a different distance.
That's not much time.
So it was different at our point, but not yours.
Okay, well, it says 1:30, is it okay? Can we do 1:30? All right, so we'll
But
resume
see,
at
Further
1:30,
away it is, the further back in time it'd be. 'Cause
and that's what we'll do.
so
So see you then at 1:30.
they're, whether it's time or space, it's all linked together.
Okay.
Yeah. How do I shut this thing? I can't find the pointer.
Yeah, 1:30. It should be safe to leave your computer there, yeah.
Okay. Yeah, I want to take this, whose computer
These are
is this?
safe here, aren't they?
I can't find the pointer. The pointer disappeared. How do you get the pointer? Yeah.
I see pointer on the screen.
Where is it? Oh, okay. But it doesn't show up on my screen.
Oh, really? Oh, look at that.
Okay, so,
I want to eject that, and I need to put the eject button.
Oh, that's a really interesting thing. It's a standard desktop or something. Just shut it down, then you'll be able to eject it.
And I don't see the pointer here either.
Alrighty.
Text someone to come and turn the live stream off, because there's no one there right now to turn the live stream off.
How do I do it? Where'd the IT guy go?
I don't know where the IT guys went. They went.
Where- Maybe just unplug it.
No idea. Yeah, that would work. If we did that, then you would get. There's your
Okay.
cursor.
All right, there it is.
Okay.
Oh, there you are. Good.